In this video, we will begin talking about our next unit called nomenclature. Nomenclature is simply how you name and write formulas for compounds. As you know, a compound is what forms when two or more elements react with each other chemically to form a new thing. That new thing is a compound. So the chemical formula tells you what elements are in the compound and how many atoms of those particular elements there are. For example, Al2O3 means that 2 aluminums and 3 oxygens combine to form what's called aluminum oxide. In this one, we have 3 elements. We have a potassium, 1 manganese, and 4 oxygens. This forms what's called potassium permanganate. And throughout this section, you will learn the rules for writing the names of these compounds based upon the formulas, and vice versa, being able to write the formulas from the names. First thing you must be able to do to write a formula correctly is know how to determine the oxidation state of an element. And the oxidation state is simply how many electrons the element either gains or loses, or in the case of a covalent compound, shares. We'll talk about that a little later on. So as we learned before, metals are going to have a low electronegativity, and they want to lose electrons. So they will become positive, whereas the nonmetals, they have high electronegativity, so they are going to gain, and they will become negative. So aluminum with 3 valence electrons, since it is in group 13, it will lose 3 of those electrons and become a +3 ion. Whereas sulfur in group 16 will gain 2 to go up to 8, and that becomes a -2 ion. And once again, the reason why these do this, for example, the electron configuration of aluminum, 1s2, 2s2, 2p6, 3s2, 3p1. So aluminum has 3 valence electrons on its outer shell, these 2 from S and this one from the P. So it's going to lose these 3 electrons. They will go away. And now its electron configuration is the same as the element with 2, 4, 10 electrons, which would be neon. So aluminum here will lose those 3 valence electrons, and it will drop down in energy level to be like a noble gas, because all elements want 8 electrons in their outer shell. Whereas something like sulfur, which is 1s2, 2s2, 2p6, 3s2, 3p4, it has 6 valence electrons here and here. Now this is much closer to getting up to 8 than it is to dropping down to 0 like aluminum did. So this will gain 2 more electrons in this 3p7 level. That will become 3p6, and then it will have an electron configuration just like argon, once again another noble gas. So this positive oxidation state simply means that the element has lost electrons, and the negative oxidation state means that it has gained electrons. Here are the oxidation states, and you'll notice that this corresponds with the number of valence electrons. So groups 1, 2, and 3 are all metals, except for boron here, the only metalloid in group 13. So these will all lose their valence electrons. So all group 1 members will have an oxidation state of +1, meaning they will always lose that 1 electron. Group 2 will always lose their 2 electrons, and group 13 will lose their 3 electrons. Once we get to group 4, though, they have 4 valence electrons, so they're going to be equally as likely to either gain 4 more or lose 4 more. And in fact, 2 of the group 14 elements are metalloids, silicon and germanium. So these are going to sometimes share characteristics with metals and with nonmetals. But tin and lead at the bottom are metals, and carbon up top is a nonmetal. Once we get to the other side, though, for groups 15, 16, and 17, this is where our nonmetals are located. And as you know, nonmetals want to gain electrons. They have a much higher electronegativity, and they're closer to getting up to 8 than they are getting down to 0. So group 15 members have 5 valence electrons. So they're going to gain 3 more to get up to their 8. Just like group 16 with 6 will gain 2, and 17 will gain 1. So these just mirror each other on the other side of 14. So this should be pretty easy to remember. These will get down to 0, and these will go up to 8 based upon their valence electrons. As I mentioned out here, there are other scenarios. We'll cover those a little bit later on. So you'll notice once we start writing formulas that if you take the oxidation state of a particular element and multiply it by the number of atoms of that element, you will get the total number of electrons both gained and lost. And of course, these electrons have to balance out. In order to form the compound, the same number has to be gained as are lost, and you'll see how this works out when we look at the formulas on the next slide. Just a note down here, by convention, we're going to put the positive element first and then the negative element second. So for most cases, this corresponds with a metal first and a non-metal second. So starting here, if I ask you to identify the oxidation state, I just want you to tell me what the number of electrons gained or lost for the element is. So for aluminum, this was already one of our examples. It's in group 13, so it has 3 valence electrons. It will lose those 3, so its oxidation state will be +3. We show that as a superscript above the element. That right there means that aluminum has an oxidation state of +3. Now oxygen over here, it's in group 16, it's going to have an oxidation state of -2. So this is -2. Notice that this number corresponds with this number, and that this number corresponds with this number. That's in fact how the formula gets written, and we'll talk about that later. When you take this oxidation state of aluminum +3, that means that each aluminum atom will lose 3 electrons. And there are 2 aluminum atoms, so 3 times 2 gives you 6. So there's a total of 6 electrons lost. Those 6 electrons have to go somewhere. They're going to go join the oxygens. So each oxygen atom will gain 2 electrons, and there are 3 oxygen atoms, so -2 times 3 gives you -6. You have to have the same charge gained and lost. These will add up to 0 in a neutral compound. So just like we had neutral elements that could become positively or negative charge forming ions, we could have charge combinations of atoms. That's called a polyatomic ion, which we'll get into in the latter part of nomenclature. Now I'm going to move on to carbon dioxide. Now carbon is in group 14, which means that it could be for the most part, +4 or -4. Which one do you choose? Notice I put this hint up here to start with the negative element. That's because sometimes the positive element can have a variety of different oxidation states. However, the negative is only ever going to have one choice. So oxygen, like we already said, is always going to be -2. That means that with 2 oxygen atoms, each having a -2 charge, we have a total of -4. So 4 electrons have to be gained. This is going to help us determine the oxidation state of carbon because these 4 electrons have to come from somewhere. And since there's only 1 carbon atom, notice that there's no subscript, so we can only assume that it's 1. If there's 1 carbon atom and we need 4 electrons to be gained, that means that that one carbon had to lose all 4, so it has an oxidation state of +4.